Hello everyone and welcome back to Tears of the Kingdom. Today is a bit different from other episodes. Instead of trying to complete a physics challenge, we are trying to understand in-game physics. So, if you've watched previous episodes, you'll probably remember this interesting object, the zonite railing, which is very suspiciously light and falls to the ground very, very slowly. And it's not very well understood why it does this in-game. Now, intuitively, it feels like air resistance is what's causing it to slow down. But I want to test that to be sure. So I've prepared various objects here that we can do testing of whether it is indeed air resistance or something else going on, because evidence that other people have collected have indicated air resistance might not be a sufficient answer. So let's get to the testing here. So the first test, I want to test as directly as possible if this is air resistance. So I have prepared two objects here. One is a sled with 8 of these railings sticking straight up from it. For standard air resistance, we would expect it to only depend on the surface area exposed and the speed at which something falls. You'll remember that from previous episodes. So when I have them all pointing up like this, we aren't exposing any more surface area downward. So we should see this falling just as quick as a normal sled. Now I can drop it right there. You can watch it fall. I can drop another sled. You can watch it fall. And you can probably intuit that the regular sled seems to be falling faster, but it's best to try to compare that as directly as possible. So the best way I've figured out to do this is take one sled we'll be using as a platform, hold it up in the air for a few seconds, then slowly lower it back down, then place the other thing, the thing we expect to be lighter and fall more slowly, on top of it, balanced well enough that it won't fall off. Use recall on the bottom object to lift both of them back up in the air. You can't do this simply with Ultra Hand. Oh, yeah, you can see it's tough to balance it correctly there. You can't do this directly with Ultra Hand as it doesn't allow you to lift up an object that has another object on top of this. The reason they did that is they don't want you to create a flying machine too easily. So this might take a couple of tries here. Lifting it up slowly has the best chance of it, whatever's on top, not falling off. And also, of course, balancing it well helps too. Okay, that looks good. I'll release recall, and you can see them fall. And it is very obvious that the single sled without anything attached falls faster than the sled with the 8 railings on top of it. Now, so the railings do seem to be slowing it down somehow, even though you would think air resistance shouldn't be too much of an effect. But let's try another experiment. Let's compare it to a case where we have all of the railings spread out. So if you compare these two objects, they have the same total mass, same amount of objects, same total density, but the surface area in the direction of travel is very different. One is basically maximized and the other is minimized. And so we wanted to see if one of these will fall faster than the other. So what I'm going to do this time is use this one with the small surface area on the bottom, since if air resistance behaves as we expect, this will fall faster. I'll use this as the platform and set it up for recall. And then I will balance the other one carefully on top of it. Might take a couple of tries here, but I'll do my best. Okay, is that stable? Looks pretty stable. Alright. Let's try recall now. There we go, and test. And they seem to fall at almost exactly the same rate. Now, even though it wouldn't make physical sense, there's a chance that the one with the large surface area actually wants to fall faster than the other one but can't. So let's, for purposes of completeness, test that as well. So we'll do the same thing, just using this as the base. I'm not setting these tests up so that we can get firm distances. These are all just comparative tests, which is good for finding some intuition, but if we want to do firm calculations, we'll need a better setup than this. But we can move on to that if and when we decide we need it. Okay. Oh. Yeah, I kind of fumbled the release there. You can still kind of see the results, but I'm going to do it again just to be sure. It looked like these two are indeed falling at the same rate. Okay. And let's try this again. There we go, release. Yeah, okay. So, testing either way, the two of them fall at the same rate. Now, one more thing I want to test, although it's a bit trickier, is what about balance? And this one we can do just by taking these off if we don't want to do a solid test. Since the railings are the things that fall less than the sled, what if all of the railings are on one side? Do we see it tumble as it falls? Yes, we do. Okay. So, whatever's going on here, let's just do that tumble again. I think it's safe to say that the gravity isn't acting on the whole combined object, but it's acting on each individual object. And when you have more acceleration on the sled than on the railings, you get the tumbling that it effectively turns. It pulls the sled down much faster. So I think that is useful to know, that you want to treat the gravity and whatever you have acting on each part of your build independently. Okay, let's go to some other tests to try to figure out what's going on here. First, let's test scaling. So here I have a sled with one railing attached, and here's the sled from before with 8 railings attached. And here's a double lifter, so we can put them both up side by side and compare as they fall. So I'll lift this up to prepare the same recall trick. And put each of these sleds in one side of it. And recall now. And release. Okay, that's definite result here. Which, if you think about it a bit from the perspective of individual things having individual forces, probably makes sense. But for the overall build, what we're seeing here is that there is scaling going on, in that you get the least amount of gravity overall when you have the most objects with low gravity, or the most light objects. I put light in quotation marks as this isn't something that works specifically with mass. So let me show you another experiment to demonstrate that. In my auto build history, I should have a couple of tumbleweeds back here. Oh, no, I lost them. So I'll pick those up at the end so I don't have to rebuild everything. And I'll show it to you later with the sleds. You can look at the chapter select if you want to skip ahead. But basically, tumbleweeds are very light and yet still fall like a rock. For now, let me take something else that is light and that you might think would have air resistance but doesn't. Korok Frond, a literal leaf. And let's drop this. Yeah, that drops like a rock. It doesn't drop like a leaf. And we can see the same thing if we do a setup where we put it in a sled. Yeah, it just falls directly with it. It seems the slow falling is limited to extremely few objects. There's these zonite railings, a glitched object, where I'm not even sure exactly why they are glitched in this way. You would expect a glitched object to have default behaviors, since if they weren't expecting anyone to use it, they would just leave the defaults in. So maybe the default is very low gravity. That seems a strange choice because it would require you to change the gravity for everything else. It would make much more sense for the normal gravity to be the default, and if you wanted low gravity, have that be an override value. So I'm not sure why that might be the case, but there is one other thing, well, two other things actually, that seem to have this odd anti-gravity behavior. And that thing in quotation marks, and I'll just take it out here, is a pair of stabilizers connected head-to-head. So, stabilizers, well, let me just demonstrate on their own. Stabilizers turn themselves upright, even if you do something that would knock them over. They'll come right back up. Very useful for many things. Now, what do you suppose will happen if we put them head-to-head? They flip over onto their side, where they kind of balance out. Here they balanced at an angle, fighting each other to turn up. But what's weird is that when they're in this state, specifically when they're turned on and fighting each other, they have lower than usual gravity. So, comparison, if I turn them off, they fall like a rock. So, let's do some experiments on these. So, first experiment, let us just do one sanity check to show that we're not just imagining the slower speed. Dropping this on top of a sled to show that it does indeed fall more slowly. And yeah, that is noticeably more slowly. Okay. And then, for completeness, a test when they're turned off. To show it's not the stabilizers themselves, but the stabilizers in the on state. And yeah, in the off state, they drop exactly the same as a sled. So let's do some comparative tests of how they fall once you connect them to objects. So we'll use our double lifter again. We will set up, in one case, 2 stabilizers on a sled, which we will turn on for the test. Actually, we're going to have to recall that first. So let's just get everything ready to put on after we've done the recall. In the other test, we'll have another pair of stabilizers on top of the sled, but not connected to it. So they'll just be laying like that, although we will have to put them in one piece after the other. Okay, so let's prepare the drop. Turn them on before putting them in. Okay, that's on the left side. And then on the right side, we have stabilizers disconnected from a sled. So the left should behave as one solid object, the right two separate objects, and we want to see how each of those three things compare when they fall. Alright, and let's drop. Yeah, so we kind of see the scaling here too. The existence of the sled weighs down the stabilizer pair, pulls it faster than the two stabilizers on their own, but not as fast as a sled on its own. So again, I think the best theory to describe this is gravity acts on independent objects in a build, and they apply forces to each other to pull the rest of it along, which then calculates out an average motion that way. So probably at the end of this, I'll think out some equations that might describe this. Now, I want to show you some other interesting things here. So one other test I did is in addition to testing with 2 stabilizers, what about 4 stabilizers? Does it scale when we do it that way? So let's do this test same way as everything else. So now we've got sled with 2 stabilizers and sled with 4 stabilizers. You would think from everything we've seen up to now that the one with 4 stabilizers is going to fall more slowly than the one with 2. But we haven't tested the scaling that thoroughly with stabilizers yet. So it's best that we do so for sake of completeness. Yeah, I know, let's put them across. I think that'll fit best. Yep, there we go. Okay. Alright. Prepare the recall. And place our sleds. Okay, everything's on this time. So we should see the anti-gravity, and let's test. Yeah, so in this case, we actually don't see the 4 stabilizer case falling any more slowly than the 2 stabilizers. Now, for completeness, maybe it's the weight of the stabilizers canceling things out. So let's get out a couple more stabilizers, which we'll put upright here, so they won't be causing any extra force on the system, but will be contributing their weight to it. And so on the left, we'll have same weight as on the right, but the right has 2 pairs horizontal to each other, and the left has only 1 pair horizontal to each other. Okay, let's test again. If you're wondering why things are breaking apart in the background, it's because I'm hitting the limit here for the number of fuses that can be active in a given area. You can only have 21 fuses active around you, or the oldest ones will start to break apart. Okay, I remembered to turn them on this time. Let's test. Same weight on each side, different numbers of paired stabilizers. Okay, yes. So we do see on the right that with 2 paired sets of paired stabilizers, it falls more slowly than if you only have 1 set of paired stabilizers. It was just an illusion before that things ended up, the math worked out so that it was the same with 1 as with 2. Probably the reason for that is these stabilizers are so massive that adding extra sets of paired stabilizers doesn't have as noticeable an effect on the pull motion of the system, because you're also adding so much more mass at the time you're reducing gravity. You get most of the benefit from the first set. Okay, so now let me, for completeness, show you where to get Tumbleweed for our test and explain why it's useful. So, easiest place I've found is to go to the Gerudo Canyon Skyview Tower. Once you arrive here, go forward a bit and look straight down. Just below us, around the trees here, you will see a bunch of tumbleweed. I'm going to take 2 of these and fuse them to each other. But for now, we can just do some eyeball testing. Dropping tumbleweed, it falls like a rock. Now, the reason tumbleweed is useful is that aside from the zonite railings, it is the object in the game with the lowest known mass. It has about 1/12 the mass of Link, or 8 times the mass of the zonite railing. But you can see here, we don't really even need to do the testing. You should be able to eyeball it that these are dropping very quickly. So whatever's going on with the calculations of falling for a non-glitched, very light object, we still see it falling with the full acceleration of gravity. So it seems to be very, very normal behavior that things always fall the same. Nintendo didn't deliberately put in air resistance for any normal object to slow down how they fall with gravity. Link has some odd behaviors when he's falling with all the diving mechanics, but he's hardly a normal object. Tumbleweeds are the lightest, least dense normal object we have, and we see no effect from gravity. You can see them being caught by the wind, so it seems the wind is a separate effect here from whatever slows down objects as they fall. I don't think it's necessary to do any further tests with the tumbleweed, so I think I will leave it here for the test and spend the rest of this video doing some discussions of how I think the math might be working out for how things fall together. Alright, so if you're not interested in that, I'll see you later. If you are, let me switch over now. Okay, before we start, let's go over some very basic equations of motion. The most important one is force equals mass times acceleration, which you can also rearrange to say that acceleration equals force divided by mass. And acceleration is specifically the rate of change of velocity with respect to time. I'm just notating that in calculus here. And velocity is the rate of change of position with respect to time. So you probably have a good intuitive understanding of what acceleration is here. So if you don't understand the calculus, don't worry, just go with your intuition. That should be fine. It's something we encounter enough in everyday life. So basically what this equation says is a force is an effort to move something. If you apply that much effort to an object with high mass, since we're dividing by high mass, we get low acceleration. If you apply that much effort to something with low mass, since you're dividing by a low value, you get high acceleration. Now, for gravity, if you go to the full Newtonian gravity, you get the force of gravity equals negative g, the gravitational constant, times mass of object 1 times mass of object 2 divided by r squared, where r is the distance between the two. And if you want to get the acceleration from gravity on, let's say, object 1 here, you would take that force and divide it by the mass of object 1, or in that equation, negative gravitational constant times mass 2 over r squared. Now, in everyday life, you're not varying your height from the center of the big source of gravity near you very much. So that'd be Earth, and Earth's mass isn't varying very much. So often we just say that all of this is a constant called g. This is the acceleration due to gravity at whatever height you're at on whatever planet you're on. And specifically negative g because it pulls you down. Now, in the game, though, I suspect what's going on is that this g, where you'll notice here, is equal to what we have up here. Notice that this depends on the mass of the planet, m2, but it doesn't depend on the mass of the body that's accelerating, or really any property of the body that's accelerating. It's purely a function of space and the other thing causing gravity. I suspect that what's going on in the game, however, is that this g is not a constant, but is allowed to be variable so that they can tweak gravity when they need to cause a desired effect. So that is to say, the gravitational constant is dependent on the object in some way. Maybe that's not the best way to write it. Let's say G1 or G2 or ... depending on what they want to do. So a very common example of this is if you go to an old platformer game, you've got ground, pretend that's not a slope, and you've got a player character who, imagine he's in plumbing overalls. Now, this player character will take a jump and go up, and then be up in the air, and then start to fall. Now, since in games you can jump a lot higher than you can in reality, like this player character is jumping so their feet end up higher than their head started. If you have normal gravity, this can end up feeling very floaty. So one of the things they'll do is, first of all, enhance gravity. But one other thing that feels nice is if the gravity differs depending on if you're rising or falling. So for instance, when you're rising, they often want a softer rise. So let's just say g equals 1 here. And here you want a sharper fall. G equals 2. So if you've got Mario or whoever it is, when they jump up, you've got a soft rise where you can have more control over it, but then they come down with a harsh stomp. So once you've accomplished what you want for a jump, you aren't waiting so far, and there's a good feeling if Mario happens to land on a Goomba. You get a nice satisfying stomp as you're coming down harsher. So changing gravity in a game is very common, has a long history. So what I suspect Zelda is doing, for whatever reason, is changing gravity for different objects. And there are 3 objects in the game where this seems to be happening. One is the zonite railing, where g equals, let's say just for point of argument, 0.1, and we'll say that's gz. Another is the paired stabilizers. And that doesn't seem to be as dramatic, but we'll say gs equals 0.2. I'm just guessing at numbers here. And the final object is the hover stone. And we'll say gh for hover is 0. Now, one comment here for the paired stabilizers. I suspect it isn't actually the pairing of them that causes this low gravity, as Nintendo probably wouldn't program this into the game to deliberately have paired stabilizers cause low gravity. You don't see them doing this in any of the shrines. This doesn't seem to be an intended mechanic. Rather, what I suspect is that it isn't the pairing themselves, but simply one sideways stabilizer that has this gravity. My guess is that Nintendo figured out that reducing the gravity on a stabilizer would be useful for having it do the stabilization. Now, another note about the hover stone is I don't think it's as simple as just having zero gravity. Because you can put other things on top of it, and if they're not massive enough, the hover stone won't fall. It only falls if there's enough force to exceed some threshold. So there is some force on a stabilizer that holds it in place, in addition to simply having zero gravity. And it could be that they don't actually modify the gravity at all. They just have this extra force. So here, I'm going to put a question mark. We'll have to do more experimentation to see if, for instance, if it's easier to move a stabilizer down than it is to move one up. That could solve the question here of hoverstone. If it's easier to move a hoverstone down than up, that'll solve the question of if it truly has zero gravity or if it just has some internal restorative force. But for now, let's just put that aside and not worry about it too much. And now, I will note there's one other thing in the game that does seem to have lower gravity, and that is in Arrow, specifically in Arrow in flight after being launched from Link's bow. And in this case, the gravity seems to be about 1/4 of that of anything else in the world. Now, this is only in flight. When an arrow is just lying around the ground, it behaves like any other object. But when it's in flight, it has lower gravity, and I suspect that the gravity modification might have even been put in specifically for arrows, as the in-game gravity was causing them to fall too quickly. They wanted arrows to fly a bit straighter, so they put in lower gravity for the arrows. And maybe that they also later found, oh, this helps for stabilizers too. Now, I really don't know why this would affect the Zonite railing, because as I said before in the video, you want the default to be a sensible value, and anything glitched that you don't think people would look at would probably use the default. So why would something glitched have a value of gravity that is very different from what seems to be the default for everything else? If the default is 0.1, as we see for the railing, then that's a lot of work to test absolutely every other object in game to make sure that somebody remembered to properly set the gravity. Which, yeah, maybe it could happen. Maybe they had a default small value and they wanted to, and they went in to modify it to the same thing for everything else. It just, it doesn't seem right to me. I can't rule it out, but I don't really know what's going on. Okay, let's talk a bit about combined objects now. So let's say we have a combined object where we have one block. I'll shade it in. It's a solid block, but I'm not going to bother to shade it in every time, attached to a Zonite railing. And you've got one fuse point here. So how do you think the game simulates this? Well, remember, we saw from our tests in the video that what's going to happen to this over time is it's going to tumble on its side. The block will fall faster than the railing, and it will tumble over. So one thing we can say doesn't happen is the game does not treat this as just one object. It treats it as two objects which are connected together. So let's go to a high school physics tool called the free body diagram, where we basically draw each object individually along with all forces acting on it. So first, with the block, we'll have one force down, which will be gravity. So the force of gravity is going to be the gravitational acceleration. We'll say G naught here for the default gravity of everything in the game, times the mass of this. We'll call this M1 for whatever the mass of the block is. And over here, there will be some tension force, where we don't know exactly the direction or the magnitude of it. That's something we'll have to solve later. This is the force caused by the connection to the zonite railing. And then for the zonite railing, we will have Gz times M2. And for the gravitational force, as well as some tension force on it, that's caused to it by the connection with the block. So the question here is, how do we solve what the final acceleration is going to be with all of these unknowns? So let's start with using what laws of physics we can. So the most useful is Newton's third law of physics, which is for every force, there's an equal and opposite force. What that's saying is that any force you apply to something, like the tension here, will have an equal and opposite force back. Or what this is saying is that T1 is equal to minus T2. So we can simplify that a bit. We only have one tension force. We'll ignore the 1 there, the 2 there, and just put a minus sign there. Okay, next step, let's start with some equations. And we're going to split everything up into the two dimensions, the x dimension and the y dimension. So it's going to be easiest to go to another page here so we can clearly write things. So on the top left, we'll do x dimension for the block. So ax1 is going to be equal to, well, if you remember before, gravity doesn't have any x component, so that's just going to be the x component of the tension divided by m1, and a y1. Okay, here we have gravity going down, so we've got negative g naught times m1, and then we've got some unknown component of the tension plus tx, all of that divided by m1. If you want, we can cancel it out here. I'm not going to bother right now. Okay, so what's the acceleration of the zonite railing? So ax2, well, again, no x for the gravity, and the tension is the opposite of before. So negative tx divided by m2. And what's the y acceleration going to be? Well, we've got its own gravity, and we can do the same thing with the tension. So negative gz times n2 minus, instead of plus, the y component of tension. Oh, forgot the equal sign there. All divided by m2. Okay, so this is our full set of 4 equations we have to work with. Now, before trying to solve it, which, again, there's a lot of variables here, let's count up our known values and unknown values. So I'm just going to switch to a different color here, and we'll highlight what are the things we're trying to solve for and what are the things we don't know. So masses, so M1, I'll circle it everywhere. All the masses are known. Those are fixed values, which we can just imagine we made a scale or something to calculate what the mass is. Gravity, that's known. We can do tests of things falling to figure out what the gravity is, measure it very directly. And then switching colors again, the unknowns are X tension and Y tension. Oh, looks like I made one mistake there. That should be a Y on the left. There we go. Okay. And then similarly, all of the accelerations are going to be unknown. So circling them again. Okay, then count up our knowns and unknowns. So we have 4 different accelerations and 2 different tensions. So that means we have 4 equations, but 6 unknowns. Okay, so if you have more unknowns than equations, you can't solve the system. If they're equal, you can solve it. If you have more equations than unknowns, you can solve it, but you might get contradictions if you weren't careful in deriving things. But more unknowns than equations means this is currently an unsolvable system. So what happens in reality? And how can we get more equations to solve what's going on? What do we think's going on behind the scenes here? Well, the first thing is that we have a rigid body here. These 2 objects are connected pretty solidly. So what that means is that the overall motion of the 2 is going to be something that will keep the 2 tightly together. And there are a few ways this can happen. What I suspect is the most likely way that happens is if the tension force that we have here depends directly on the separation between the 2, which is to say, it's going to depend, at least to second order, on all of the accelerations. As if the 2 things accelerate differently, they'll pull apart a bit, and then the tension will depend on that. So if I were programming this, here's the way I would program it. I would say that tension, which I'll put as a vector right now, is going to equal some spring constant with a minus value that the tension will pull things together times the separation between 2 things as a vector. Or splitting that up, I would say that tension in the x direction is going to be the opposite of the difference in x position times the spring constant, and tension in the y position is going to be the same spring constant times the difference in the y position. So this is what I think is going on. Nintendo has a pretty high spring constant to keep things stuck together. There is some maximum allowed tension that if the tension ever exceeds that, the 2 things will break apart, which you can see in game if you try to attach something too heavy to a joint that can't hold it. You'll exceed this tension. Now, you don't see these stretch too much, but you can see it stretch in some circumstances. For instance, if you have 2 stakes in the ground, or rather, let's start with 1 stake. You have it fused here to another object. This object fused to a stake. And then you pick up a stake with the Ultra Hand and put it into the ground just a bit away from this second object. The fuse will pull out to get to these, stretching out the fuse, and it will also stretch the gap in here out a little bit, allowing it to spread apart. And then if you detach the stake or move the stake out of the ground, it will pull back together. This is a technique known as stake nudging, which increases the tension in a joint. You can only increase it a small amount before it breaks, but one neat trick, which I won't get into here, is that if you store the creation in auto build and then rebuild it from auto build, the game forgets about that tension. And so, yeah, I'm getting on a sidetrack here, but this is actually extremely cool. If you store what you've made in auto build, rebuild it with auto build, put it back in, you can stake nudge again, pulling it another step away. Auto build again, pull it another step away. Auto build again, pull it another step away. And eventually, you will have something that looks like this, where the connection between the two is spread out over a long distance. Doing this enough, you can get arbitrarily long connections between anything. The way the spring thing seems to work is it's the difference in distance from the original default position, and any movement of that seems to cause a restorative force. And you get a restorative force in both the X and Y dimensions. Now, when you auto-build, it resets where the original position is, which allows this stake nudging to pull objects apart. There are other guides on this. I just had to bring it up now because it was so close to what we're talking about. But anyways, let's go back to our equations of motion for what we have. So I'll just draw up what we have again. We've got a block. We've got something attached to it. And we have 6 equations of motion now. We've got 4 acceleration equations and 2 tension equations and 6 unknowns. The 4 acceleration components and the 2 tension components. So we have a solvable system. Now, that will just give you what's happening for a moment. But we can talk about what happens at that one moment. So let's imagine the moment when we initially release this. The tension is going to be at the default state. So in the default state, tension is going to be 0. So that means we don't have any X components to acceleration, since only tension causes X acceleration. We only have Y components to acceleration. So this gets simplified tremendously. So we can just say A1 equals negative G naught, since this has the normal gravity, times mass 1 divided by mass 1. So force divided by mass, or mass just cancels. A1 is negative G naught. And then similarly, we can just skip over the mass for the other ones. A2 is negative GZ, a smaller value. So for the first moment in time where tension is 0, this block is going to accelerate a bit more. And you can imagine that the gap between the two isn't going to increase much at first. The velocity is 0, so changing the acceleration will change the velocity, but it won't be until a few moments ahead that the gap actually starts to widen. So at first, what's going to happen is this will drop a lot and this will drop a little. And the difference in how they drop will cause this to turn. Now, as this pulls ahead, you can see if this is moving more than the zonite railing, then the gap between them will widen. So let's imagine we are a few moments ahead. We have the block there and the railing a bit above because it hasn't fallen as much yet. And we have tension like this. So the tension is calculable from the gap. So we have Tx. Remember, the equation is Tx equals minus spring constant times delta x. Well, here we've only fallen vertically, so we're not actually changing the x component as much. And so that would theoretically be 0. And Ty is negative spring constant times delta y. Now, hold on for a second. Okay. Yeah, and this, you can probably tell by the way I'm talking, this is where I realized this isn't quite right. I was oversimplifying the way springs work. So I think we actually have to complicate it a bit because this isn't right. We don't have 0 force in the x direction. We have a bit more than that. So I think the way this works, the proper version of Hooke's law with vectors looks something like this. The magnitude of the vector t is equal to, well, actually, we don't have a minus sign here. Well, that goes into the direction. So it's just going to be the constant times the magnitude of the change in the position vector, and the direction of t. Now, I'm not sure what the standard way is to denote the direction, but yeah, I think one way to do this is t vector over magnitude of t is equal to minus displacement vector over magnitude of displacement vector. So I think this is the proper vector form of Hooke's law, which does notably differ from the way I broke it up before. The way I broke it up before was incorrect. I apologize for that. I'll have to put an editing note saying that I'll later realize it's incorrect. So what this means is that if you stretch a spring, like let's say you have a spring, you stretch it in the y direction, you will feel some restorative force in both the y and x directions. It'll always be opposite the direction you pull it. So let's say we have one spring looks like this. This is the default state. Then let's say you stretch it out down like this. You're going to feel a force in this direction to restore it. Even though you haven't changed the x displacement here, so that'll just be like delta x, you will still feel a force in the x direction, which will be non-zero. So actually, if that's just, so the difference here, delta x is 0, but in this case, tension in x is not 0. So this is the proper form for what's going on here. So let's backtrack. Let's go to what we actually have for the objects that are falling. You've got our heavy block, and you've got the zonite railing. So gravity is going to be, as before, pulling the block more than the railing. So what does the tension look like here? So the tension on the block, Tx1, well, the connection is stretched out a bit, so it's going to be positive. I'll just say equals plus to say it's in the positive direction. We don't need to worry about actual values. Ty1, well, it's stretched out and it's trying to pull it upwards, so that's also going to be positive, whereas gravity's pulling it downwards and is negative, so we'll say gy1 equals negative. And probably gravity is going to win out. And so we'll just say greater than ty1. More negative than ty1 is positive. Now, on the zonite railing, we have tx2. That's going to pull it a bit to the left. That's going to be negative. ty2, well, that's going to pull it down, so that's also going to be negative. And then gravity, as always, pulls it down. So, putting these together, in the x dimension, the block is going to be moving to the right. Gravity's still going to win out, so it's going to go down, though a bit slower than before. The zonite railing, in the x, it's going to go to the left, and gravity's going to pull it down a bit faster than before. So once these two start getting separated, we'll see two things happening. So drawing this again, so I have more space to work with. One is that this block is going to go right and the railing left. And two is that the railing is going to accelerate a bit faster and start catching up, while the block accelerates a bit more slowly. So the next step after this is that the whole thing, with the block being below and going right and the railing being above and going to the left, is that the whole thing will start to rotate. So the next step will look something like this. Where the whole thing has rotated. We see it tips over to the side due to the forces that we've described. Now, this is going to happen again. Once the tension equalizes a bit, you're still going to have more gravity on the block, and so the block will still fall a bit faster. That'll increase the tension. Then the tension will try to catch it up, but it'll do that by rotating things, and it'll eventually equalize when the whole thing is about vertically. So then let's think, okay, what's happening when everything's vertical? Okay, so in this case, all of the x components are going to be 0. There's no x force in the tension or in gravity. We can just work in y. So starting with the block, so acceleration y of the block is going to equal to, well, first we've got gravity, negative g0 times m1, and then we'll have some tension. So if this is normally going to fall a bit quicker than the zonite railing, so it's going to stretch the connection a bit, so we'll get some tension upwards. So we'll say plus ty, which is going to be some positive value, all divided by m1. And then for the railing, we will have negative gz times m2, and now the tension is going to pull it down, minus ty all over m2. And once this reaches equilibrium, this is going to mean that ay1 will actually equal ay2. It's going to fall just enough that the two are separated a bit, that there will be tension in the joint connecting them, but this tension will be enough to equalize out the gravity forces. So essentially what we're going to get in the equilibrium state is that ay1 equals ay2. And once we put this in, we have, let's see, we have 3 equations here and 3 unknowns. Oh, whoops, I accidentally cleared the screen. So I decided to draw everything up in a way that I think illustrates this a bit better. So on the left side here, we have the zonite railing with the 2 forces acting on it. These combine to give acceleration A, which goes downwards, which is equal to negative, because it goes downwards, gz plus ty over m1. That is, it goes downwards a bit faster than it would under just its own gravity because of the tension from the connection between it and the block. Now, secondly, we have the block. It has one force down, that's its own gravity, and one force up, that's the tension. Now, in equilibrium, it has to be traveling at the same rate as the zonite railing. So this A is the same, and this A, also negative, ends up being a bit less in magnitude than the G naught it has normally, because that gets decreased by the tension pulling it up. So this is how things equilibrate and why these railings have an apparent anti-gravity effect. They aren't reducing the gravity of things they're attached to, it's just that they fall more slowly, and so they cause a tension force in that other things have to drag them along. So they have something like a parachute-like effect, except instead of the parachute being caused by wind resistance, it's caused by these railings having their own lower gravity. Now, they don't change the gravity of what they're attached to, they just hold them back because the other thing needs to apply more tension to drag them along, since gravity doesn't affect them as much. Okay, well, I hope that was clear to everyone. Thank you very much to everyone who's watched, and if you have any questions, please do let me know in the comments or anywhere else I linked this. And if there's enough confusion, maybe I'll add some clarification or do some follow-up on other related things. So thank you everyone again. Bye-bye. Thank you very much for watching, everyone. If you enjoyed this video, please leave a like, subscribe, and click the bell to be sure you get notifications of new uploads. See you again soon.